Okay, welcome to the second session. It's my great pleasure to welcome Professor Shanmuganathan Raman from IIT Gandhinagar. He is widely known for his remarkable contribution in computer vision, deep learning, and computational photography. His insights have continuously inspired students and researchers alike. He holds the prestigious Jibaben Patel Chair in Artificial Intelligence at IIT Gandhinagar, reflecting his leadership in the field. His research has been recognized with several awards, including the Excellence in Research Award from IIT Gandhinagar and the Qualcomm Innovation Fellowship. Professor Raman's work has significantly advanced the domains of computer vision and graphics, and he has mentored numerous students who have achieved notable success in academia and industry. Today, we are privileged to have him share his thoughts with us. Please join me in giving a warm round of applause as we invite Professor Shanmuganathan Raman to the stage.
Thanks for the nice introduction. Yeah. So, good morning, everyone. So, it is a great pleasure to meet you all and share some of the works we recently did at our lab, which is called Computer Vision Imaging and Graphics Lab at IIT Gandhinagar. And it's you are from different places in India and different institutes, and it's a great honor for me to address you all in this talk. So, in this next 1 to 1.5 hours session, I would be talking about some of the works we did. I labeled it as AI for post because we used enormous amount of deep learning and all these tools, right? So attention, all those tools. So, but the primary motive of this talk is to introduce to what is post lifting, what is post estimation, and what is post based tracking, and some of the state of the art works we have done in this area. Okay. And these are the works done by my students. It should be by my students, so because most of the work was done by them. So Saumiratna, Devnath, and Shashikant, who are MTech and PhD students, and I have amazing collaborators from NIMH, NIH, US, Harish Kati and Yamuna Swami. So they contributed quite a lot to these works, which I will be talking about. So CVIG lab, I will just give an introduction to set the context. So some introduction about the varied works which we do. So I will focus on this talk after some 10 minutes or so. But these are some of the students currently in the computer vision imaging and graphics lab. So these are some of the alumni. So some of them you may know. Some of them are faculty at other IITs like Rajendra, Sudhakar and Indradeep, and Alok also is visiting fellow at TAFR, and a couple of them are in industry. So if you look at the lab, we do a lot of works in different areas. So we do classical and theoretical vision before this deep learning AI guys invaded this computer vision and started dominating. So we used to do a lot of theory for computer vision with proofs and valid solution for some open problems, right? So some of the works we have done before this deep learning took over completely. And we have proposed some deep learning architectures, especially training free methods for image restoration. And we have done work for Indian cultural heritage. We have done some work on video analytics and security. We had some state-of-the-art results for action recognition in the years 2019 to 2022. And we have automated something called driving test with another company. We have worked on agriculture. We grew cotton in the campus, flew drones to study the cotton. So the data set we are recently got it accepted. We will be releasing it soon in the International Conference on Computer Vision, International Conference on Image Processing this year, 2025. And we have done some physics-based vision for life or healthcare. And we have also done some works on computational photography, especially on high dynamic range imaging and video. And this is some of the works which I will be talking about post estimation and tracking, which we did some post transfer. I'm not going to talk more about post transfer because it was done some 3 years back in ICPR, and we have contributed significantly to some of the data sets. One of the data sets is Yoga 82. I'm going to talk about it today. Some of the works presently we are interested in doing are shown below. Okay. And these are some of the awards we have obtained over time. Most of them are student awards, and a couple of them are the faculty awards. And some works I will flash so that you get an idea of what we do and set the context for the kind of work I'm going to present in detail today. Okay, so this is one of the recent works which we will be presenting in a couple of weeks in CVPR, where we solve the problem of packing, right? Optimal packing of irregular objects within larger irregular object. So we used some ideas from art called anamorphic art, where the objects are arranged and some shadow is cast, and how the shadows appear based on which you can rearrange the objects, right? So some meaningful objects you can do. So we use that idea to arrange some irregular objects to cast shadows like this CVPR 2025, which you can see here in the top, and some alphabet irregular objects are put inside a cube, right? And we are able to pack optimally up to 40% density. And there is a hippo, which is a big irregular shape, and there are smaller irregular shapes which are getting packed here. Here the packing density is 55%, and number of objects, around 220 objects we could pack inside this. Okay, so this is a problem which theoretical computer science people also attack. Some of you who are fascinated about theory, they also call it a packing problem, right? So we do it in the graphics plus AI approach. So if you are interested, you can look at it. So there is another work we presented in SIGGRAPH Asia last year, so where we try to take an image and then developed an AI algorithm which could, without training, which could create an image as if it has been scribbled by an artist. So we call it ScriptGen, which generates scribbled art through meta-heuristics. So this is one of the art papers which was presented at SIGGRAPH Asia 2024. And on the left-hand side, you have the top left-hand side, you can see another work where we did some 3 years back, where we took some CAD models or some parts of the objects, and then we built a graph neural network-based AI system which could assemble these into meaningful objects. Like one of the examples shown here is the chair, right? We had state-of-the-art result at that time, but some of them have overtaken us in the recent past. And there is another work we did, interestingly, in the same conference, where we don't have any 3D objects to start with. You are given shadows, right? So an object, a virtual object, what shadows it has to cast on the walls. That is the input to you. So can you synthesize that 3D object through AI algorithm, right? So we did it, and the result you are showing here, the animation you are showing here, or the video you are showing here, are a couple of objects which were generated by AI. There were no physical objects like that to start with. Only shadows were the input. The physical object is the one which is 3D printed from the AI generated 3D mesh. Okay, and we physically kept these two are the physical objects which are 3D printed, right? So we flashed light to verify whether they are actually casting those shadows or not. So this work is called shadow art. So it was very famous earlier. Some work came, I think around 15 years back or something, shadow art. But we revisited it in the framework of differentiable rendering, and then gave a nicer solution to this problem. And this has applications very much. You can also have some sketch of how it should appear from the top view, side view, and bottom view, and feed it to the algorithm. It can create probably a car. You want to give sketch of the top, side, and bottom. It can generate the car model. It's a 3D model, so it can be 3D printed. So another work, we have done some field works earlier, so which involve large-scale 3D reconstruction of a temple at Dwarka and some Harappan artifacts at Dholavira, Lothal. And we also have done another work which is quite unique in the sense that photometric stereo is a method to reconstruct 3D from images. You take few images with different illumination. So you have a lot of lights here. You turn on and off some selective lights, take the images, and then feed it through a classical method, which is a least square minimization. You do it, you can get the 3D thing. So, but how many images you have to take? The classical limit says that because of you can solve a least square solution only if it is properly determined or over-determined. right? So from that result, you can easily say that because it's a 3D object which has a surface normal you want to estimate, it has 3 components, right? So at least 3 images with a different illumination are required, 3 or more. So we broke that. But when breaking using learning, you can say that you show a lot of examples, the system learns and finally give a couple of images with different illuminations, which are shown here, I1 and I2, it will create the 3D. We didn't do that. We use this encoder, decoder, all those things as something like a classical thing, which has less parameters. Here you have over parameterization. That's the only way. So there is no 3D ground truth available to us. So only the 2 images with 2 different illumination settings are fed through this network. What it will do is it will first decompose the image into components. So an image is composed of 3 components. One is the geometry, another is illumination, another is the material property. So we decompose it. And first few networks you are seeing are decomposing the image, and last few layers are recomposing the image to create this image back. The input is the same as the output. So you keep calculating the error. Finally, if the decomposition and the recomposition steps are perfect or with minimal error, that way you can say that the illumination and the 3D geometry, material properties all are estimated correctly. That's the approach we used. We used the self-supervised learning approach to solve this problem, which we call it DPS2, with only 2 differently illuminated images, which broke the conventional thing. It was presented in ECCV. And one more check we do, if you look at the bottom right, you can see that one more constraint we put was you estimate the illumination somewhere here and try to illuminate the second image with the illumination estimated from the first image. That's what we are doing here, to do a sanity check, whether the estimated illumination is correct or not. So the more constraint you put, the faster it will converge to the correct thing, right? So this is the approach. So this is a self-supervised learning approach. Here also we don't have any 3D ground truth to start with. There is no training, testing or inference phase. It has only one phase. So you have 2 images are given and you get the 3D model in like the classical setting. There is no learning is involved, but it learns on the fly how to do it. Okay. So if you are interested, you can check this work. And one more work we did in the supervised learning setting. So what we did was like 2 images also. The problem is if you change the illumination, take 2 images, the objects could be dynamic, right? So in the scene, and you will not be able to compensate for that in most of the scenes, and it's a overhead. This object moves when you take the images. Because the setting is camera is fixed, the scene also is fixed or static, right? That is a photometric stereo setting. So here camera is fixed, but scene you don't have control. So what if you have only one image? How you can get the 3D? So what we did was, we proposed an approach in this last year, ECCV. So where we specify the lighting positions and synthetically relight these images. Here also we decompose the image and then relight the image by replacing the existing illumination by these different configurations to get the relit image. Here these 4 relit images can again be fed through another pre-trained photometric stereo network, which can give you more accurate ground truth. So it is a hybrid between, there is something called shape from shading or monocular depth estimation methods, which take one image and get the depth. But we gave some meaning to it, right? So we gave meaning to this problem through photometric stereo, but not by capturing or physically changing the lighting configuration when we take images, but taking one image and let the AI system illuminate it or relight it, right? And you get the data you require, because you need 3 or more images. Here you have 4 images. You feed it through a classical photometric stereo or any pre-trained photometric stereo network. You will be able to get the depth more accurately. So this is our latest thing. This is the state of the art for this framework as of now. And there is another work we did this year, like what are those lighting positions which gives the accurate depth? So the next question comes is, what are those lighting positions you need to take? With minimal lighting configuration, I take certain number of images, I get the depth map correctly. So we provided a solution. We call it illumination planning, right? So you would have seen a movie setup and all. There is a big sphere. The actor is made to sit at the middle, right? And then different lights are turned on and off, and then images are taken, and then 3D reconstruction happens, right? So something like that. So if you have a sphere, big sphere inside which the object of interest is sitting, so what lighting directions, minimal number of or optimal number of lighting directions which you need to use to take those images so that you can reconstruct it well, right? So another work we did, which won the best poster award in Pacific Graphics, is a similar thing. So it's also similar framework where it's all corresponds to image to 3D. So there is a hand shadow art, right? So the villages and all, there is a screen, and you make some positions of your hands to create some objects of interest to narrate a story. So what if a AI system trains you what hand positions you need to keep to narrate? You give a script to the AI system, and the AI system tells this object to this object I have to transition, how to move the hand to keep the position to get that. So that's what you are seeing here. Here you have a rabbit and a bird. So how the hand position has to change from going from a rabbit to a bird. This is the first of its kind. And this graph, if you see, there is a work called Hand Shadow Poser, which considers our work as the only baseline. So we won the Best Poster Award in Pacific Graphics for this work. And there is another interesting work which we did, which without using learning. So you take images. Here the setting is the camera moves and take multiple images, but the object in the front is moving. There is an object which is moving, and you take multi-view image of the scene. So using the geometric constraints, can you create a tool? Like you can see there is an eraser kind of tool running, so which erases the foreground but does not create a hole, but geometrically correct information from the background is filled. Yes. So this is called dynamic object removal from multi-view images, so which we did some time back. And we have done some work on EEG to image also. Recent past, there is another faculty called Krishna. We collaborate to create the, so when a EEG is recorded, what kind of visualization happens in the human mind? Can it be modeled? So there is the EEG to image work. And we have done a lot of symmetry works, which are classical setting. We have proved some theorems and probably got some results which are in the learning free setting, they are the best, but now the learning algorithms has taken over. Here you can see image symmetry, and there is an intrinsic symmetry where you move the hands, right? And the normal symmetry is broken. Still, can you correspond my index finger, right, with this index finger, the tip, right? Or the thumb with this thumb. So that's called the intrinsic symmetry. We had the state-of-the-art result. And there is another interesting work which we did is knot art. So you put a constraint. So here also shadows are given of what shadows has to cast. But in the earlier work I told, so it can give 3D mesh which is not physically plausible. So how do you ensure that the 3D mesh you are getting, you can 3D print? That may be disconnected components earlier. So we put something called a knot constraint. Knot constraint is you have a big rope and keep putting knots and creating some object. So it's always connected thing, you can 3D print. So here is an example where a smiley image is given as input, and we create a knot based 3D model and you light it. This is a physically, he has printed that knot structure and hung it from a rope. This is a 3D printed structure, and we shine a light to verify. So this knot structure is generated by the algorithm, right? There is no such thing exists. So we have done some work on recently on object detection and tracking for some road scenarios where we have deployed in the campus where you entered this gate 1. We have deployed our solution where we can do many things. It can detect vehicles, it can classify vehicles, it can the path of the vehicle it can estimate, and we can put some virtual lanes to count in and out vehicles, right? And also it can get the density analysis if it is a 6-lane road, so which lanes are more occupied at a given time point, right? And it can also estimate the speed with some configuration. So this is the pipeline we used. And we have two models. One is a nano model, which is lightweight for the mobile devices, which has a lesser accuracy, but we have a much better model. But the idea behind this is why it worked quite well is because we didn't have a large-scale data set for Indian setting, but we used some Dhaka and other places which are similar to Indian roads. We trained on that and tested on Indian settings. It did quite well. Okay. And now we come to the talk. So now I'll show you some historical things. So how our interest in the post. So one problem we were working on action recognition. That is one of the things. So there are some data sets which are standard data sets, HMDB and kinetics. They are the data sets which people work. And since from 2019 to 22, 18 to 22, for an example, like 4 years, we have done a lot of work in the human action recognition. So given action of the human, you need to find out, you have a video and you need to find out what action the human is doing. So it's a challenging task, and we had the state of the art during that time, but now it may be about to it. And in the same time, so some of my students, Manisha and Sudhakar, who are now faculty at IIT ISM Dhanbad, they had a postdoc at Japan. They were about to go for a postdoc, so they collaborated remotely, and Sudhakar collaborated remotely, and Manisha was there, I think. So they tried to curate a data set called Yoga 82, which can, given an image of a person doing a particular yoga pose, they curated a data set which will label it one of these 82 poses. It's a 28,000 images they labeled it, and it's a multi-class classification problem, 82 classes, and they are all belonging to some 20 super classes which are listed here, and 20 super classes are further merged to 6 classes like standing, sitting, balancing, inverted. So it gives a hierarchical kind of testing of the algorithm. So you can have an image and test it for 6 classes, which are the final super classes, but you can test it for 20 super classes also, or the 82 final classes, right? So this became very famous. So this is one of the first attempts on the human pose estimation. So here, how do you design an algorithm for this kind of a problem, right? So what you do, you normally try to build a network. Now you call it attention, right? So earlier it was called a heat map also. So the network should focus on the person in the image. There will be a lot of clutter and a lot of irrelevant information in the image. So you need to make the network, build a network and train it so that it makes the decision by attending to only the person doing this one, right? The pose. So parallelly, we did one more work which is on diving classification, which is there is a driving data set also. The diving, it's a very fast movements they do, right? So you want to classify it. So we did a work, so we had some idea about how to attend to this. So there also, there are a lot of people also will be there, right? The audience will be there, and there will be many objects and everything. Still, you need to, on the entire video sequence, you need to focus only on the person who is diving. So that is the idea. So that's where this attention mechanism comes in handy. So you need to build networks, and there are approaches which are recent, which are quite state of the art on this same data set. And that's what I wanted to say. So here are some results at the initial stages. The attention may be much better now, right? If you see in all these images, it is attending to only that person. Yes, sir. This is an application of this attention mechanism in transformer, and you can have a vision transformer, which can do this job for you also. This is one of the earliest things. So here you have an image, and the entire image is classified based on what pose that person in the image is holding at that time. Okay. So now I want to move forward. So now after this, we did one more work where it's called pose transfer, where you have a pose of a person in terms of a stick diagram given to you, right? And you have an image of the same person in some other pose. The person is lying down, that image is given, and there is a pose which is as if the person is standing. Can you build a generative model to synthesize the image of the same person in the same environment as if he or she is standing? That is a post-transfer problem that I am not presenting, but if you are interested, you can check that. That's also an interesting problem in this domain. Okay. So two works I want to talk about. One is a recent, it has been a work which went for around almost 2 years, where we built end-to-end model which can in real time not only detect the object which is moving, but also get its pose, and the entire pose is tracked. So that's why we call it simultaneous tracking and estimation of pose. Pose, what do I mean by pose of the person? Anyone? So when I say pose-based tracking, so what I should track of a person? How do you move? Anyone? Yeah. Yes, only joints? Skeletons, yeah. Bones and joints, right? So the bones and joints are tracked of any object. So we are not limiting to humans here. It's anything which moves, any living object which moves. Not at microscopic level, but at the macro level. If I have a mouse which moves, I need to track the bones and joints of that mouse which moves, right? If I have a horse, I have to track its gait. So human, different, or kangaroo, different. Different sports activities, different kind of movements. Everything I want to track. It's a universal tracker, universal pose-based tracker, right? This work is, we have put it in archive and it's under review, so you can check it, but I will present it with as much detail I can, I'm aware. Right? And another one, which we recently, last month we presented, the other work I'm going to present today is on lifting pose. What is pose lifting? So I told what is pose estimation and tracking. So pose estimation is getting the bones and joints from a single image. Tracking means propagating that or re-estimating and recalibrating it on the entire video so that the person's entire movement is tracked. That is pose-based tracking. Right? So now this another work which is the lifting, post lifting. So in the title of the talk, I have covered two of the things: pose estimation and tracking of pose. What it is, I have explained to you. I have not told how to do that. But pose lifting. So we are all living in the 3D world, and whatever pose you can estimate from 2D image is a 2D pose. This is a projection of the 3D pose onto a 2D plane. Can I say that? Right? Then what I need to do? We need to lift that pose. That means we need to lift that 2D pose detector to the 3D domain. Yes? But normally the systems are very complicated. You need to have some suit someone has to wear, do that thing, get the 3D points, and then have a video camera shoot that person who is doing some activity. So it's very much a lot of things involved. So in this work, what I'm going to present is how to generate data synthetically. So we use the frameworks like Unity to animate some avatar or asset in a 3D environment, right? That means you are rigging that avatar or asset, so you know what is the 3D pose of that person, that thing is. Then you render it as 2D, every snapshot, right? Your 2D to 3D, it is okay, you can easily render. So you will have 2D to 3D correspondence. So that's how we are going to generate the data. Then train an AI model or deep learning model, which then you can test on in the wild data. Okay, so that is the approach we are going to adopt. So that way, because humans at least will wear suits and do whatever you say. What about animals? How do you make them wear suits and everything, right? So it's a challenge, right? So we are going to show the results for two species, one macaque and one horse, and see how it performs. Okay, let me start with this first work, which is the step, we call it simultaneous tracking and estimation of pose, which is under review at IJCV, and you can, I put it in the archive for the people, because as of now, according to our metrics and everything, we are the state of the art by a significant margin compared to the other works in this domain. Okay, so let's talk about this. So again, I want to say, like, these are some of the snapshots of the results we achieved. So we want to build a tracker which should identify the object across frames in a sequence. Its pose as well as the detection box all are propagated, right? So, so existing approaches, what they do is they estimate the target and then crop it. For the example, like you first do the detection part, which region in the image the object is there, then you detect the pose in there. So we are doing both at the same time. That's why we call it simultaneous tracking, right? So we do some architectural modifications and achieve this. Yes. Okay. So this is, if you want to ask me like how the concepts of this step works, it is something like this. So we train using some frames obtained from some standard data sets, and it's a supervised setting. So we have the model optimizer which is trained on the thing, then transfer these parameters to the test frames. There is a backbone network and a target model whose parameters are shared, and then the target scores are the ones which is the bounding box as well as this thing. So we use some loss function with some regularization in our work. So how it works overall, it looks something like this. So we use some transformers and some networks which are MLPs, which we use for some of the tasks, and this is how it works. So to simplify things, I would say something like this. So this is the training this thing, what do you call training phase. You can ignore the top one. So we train this something like this, right? For some of this key point, KPS regressor and KPS localizer are for key points, and BBox regressor and BBox localizer is for the bounding box. Okay. Then what you do after you train, this GMSP module is shifted here. Only this GMSP module, whatever training has happened, that is shifted here, and this backbone network we have, which is shifted here, and then we pass it through the trained encoder decoder network, and this entire thing is there. So if you see the arrow diagram, so that's how it works. Okay, let's go one by one. So here, these are the target state encodings, which are the initial. It makes the feature available for the future encoder decoder network of transformer. And here is this model optimizer, which in the previous diagram I showed the weights are shared. So these weights are used for even inference phase. And then there is a regressor and localizer. Okay, so so these are some of the internal workings. I will not go in much detail, so I will go somewhere here. So what is present in each of the module? This GMSP module has, which you saw here, this one GMSP module. It has a network which learns something called the Gaussian map soft prediction, which infers enriched information that approximates possible target state. It prepares for the next encoder decoder state. And this is the localizer network, this is the regressor network, this is the key point localizer, right? So all of them are some convolutional and some MLPs. You can go to the paper to learn more. Okay, so there is another module called OMRA module when you have only the testing phase, which looks something like this. So finally, you have this one, this KPS regressor and key point localizer. There is a bounding box regressor and bounding box localizer. So these two manage this bounding box, and these two manage the key points. Okay. And what we did was this entire thing, the training is done here. This entire module is trained, and then we go here, and then this testing will go through only this. Okay. So the training is done on many data sets. So one is APT 636K, which has 36,000 annotated images with 2,400 video clips containing 15 frames at least, and covers 30 different animal species, which has 11 labeled key points. Right. So here, if you see, the different data sets have different labeled key points because the organism which is involved is different. And there is a APT 10K, which has 60 different animal species from 23 families and 17 labeled key point, but the number of images is bit less. And there is a CrowdPost dataset, which has 14 labeled key points for humans. And there is a DLC benchmark dataset, which has 3 species, marmosets, fish, and mouse, each with different key points. So it's a supervised training, and there is a testing phase. You do it, right? You go through the paper to understand what are the individual modules. I'm not going into the finer things. So let's visualize some of the steps. So how each object is, the key points are regressed, which is shown here, and the bounding box is marked, which is shown here. And here I will show you, this slide will give you some results, test results on some challenging videos also. So I'll make it full screen. So let's see some results on animals, this framework. So you can see some giraffe, I think kudu, monkeys, and orangutans, I think, some humans. So you see that the kind of network we designed, it handles self-occlusion. The guy is rotating. So here you can see we have initialized to only 2 persons. So some other guy occludes also, it holds on to this person, right? And you see it doesn't occlude each other also, these 2 things, right? Here here you see so many people are this thing tracked. So some more results on humans. See, it's a very challenging data set where we have a activity happening. Very cluttered data set. And there is a mouse data set. So I told like it works for different bones and joint configurations. So it works for this also. Yeah. So these are some of the results. These are some graphs. I'll skip. I'll go to this slide directly. So the idea here is we have a regressor and a localizer for the bounding box and the key points. Both help each other. That is a main crux of the idea. So other modules help it, the last modules, the 2 modules, the 4 modules I showed, right? So both happen simultaneously. So now here, if you see the accuracy level and all, the bold one is the best. So we are beating some of the things. Some of you from the life sciences and other domains, there is one more famous method called deep lab cut. We are beating that also. And there is YOLO V8 GAM, YOLO V8L, transpose. We are beating them as well in different data sets. And one thing we did, like, can we test? Because you train and test on the same data set, it is one thing. So can we check how it works on a in the wild data set, so some new data set. Here we found there is a Awaji monkey center who has a lot of monkeys. It's a center consisting to rear monkeys, right? So their data set has a lot of monkeys who do different activities, and the video feed is, I think, streamed on YouTube. So we took permission, captured the recordings for 2 days, and let our model detect the poses, detect both the bounding box and the pose of these monkeys. So as you can see, it is able to detect all the monkeys. We have hidden those faces of the human beings for the privacy purposes. And if you see, so many monkeys are detected simultaneously, and their activities are able to be tracked the poses are tracked. So there are some observations. The monkeys generally move at median speeds below 1 meter per second. Some elevated activity is noticeable during feeding episodes. It's important to note that the analysis is confined to 2D image space, excluding consideration of the third dimension. So these are some of the observations we found. So if you see the time we recorded, like November to January, so it's a 2-year-old work. So now we could complete building that end-to-end model on all data sets. It's a universal thing. So anything you give, it will detect and track across the video. And what is the real-time performance? Right? And the inference stage, we achieve a frame rate of 63 frames per second, right? So which is quite good. And so the tracking and post-estimation together, it is 63, it is giving. So we have a variant which does per frame detection also, that has some latency, but this one does far quicker. And it is useful for, so commercial cameras and all, like normally you get for 45 frames per second or 60 frames per second, it will be able to, real time it could be able to detect and track. So what is the use? What is the application of this? Right? So it has tremendous application. So the bio people are more interested, like you see this deep lab cut emerged from them. So they are useful for rehabilitation of patients who have motor disabilities or have some difficulty in gait cycles and so on. So we can use this to predict how they walk and everything over a period of time, give some treatment and everything. It could be used as an effective tool, because we are tracking only the bones and joints, and the clothing, whatever they wear, we are able to track it. That is quite useful, right? And also it is useful for wildlife management and analysis of behavior of this wildlife, right? So you have install some cameras in some, like, maybe we had shot some videos in this Kankaria zoo also. So you deploy this thing, so you can track the activities of the people per person, and the AI algorithm gives you a summary of what kind of activities that person was, what kind of things and everything. So that gives an idea, because the mind drives the activity. So what are the behavioral patterns and the interactions between the animals who are confined in some space? Even you can install it in the forest also, but monitoring it will be difficult. Any confined space, it's quite good. Like even Vantara and other places, they can easily use it to understand the interaction between them. So it has not only it's useful for some stakeholders, some neuroscientists are much more interested to study the behavioral patterns of the animals, as well as humans. So sociology and psychology people also will be interested. Like the Harish, who is the co-author, the collaborator for this work, he's a neuroscientist. So he is interested in, for his studies, it's quite useful. So it acts as a tool for their several of their hypothesis testing and other things. So this is the idea. So we are in the middle actually. So the accuracy is quite good, and we are in the middle, but it does quite well. In the terms of frame per second, 63 is quite good. Okay. So some more things. So in conclusion, it's a novel work for simultaneous tracking and post-estimation across different animal species. The method jointly estimates the pose and tracks the objects of interest using a transformer-based discriminative target model prediction approach. The key contributions are two things. One is the Gaussian soft map prediction and offset map regression adapter module. These two modules are the things. So which they effectively remove the dependency on key point initialization to estimate. So you go through the work to understand better what is actually happening. So in the traditional top-down approaches, you need to detect per frame. So we are detecting and propagating also this network. So it works quite better and faster than the traditional approaches. And it achieves state-of-the-art performance in both tracking and post-estimation. And we have evaluated it on challenging scenarios and in the wild settings, and shown and observed that it works quite well. Okay, so I'll pause here. So any comments or questions, queries to take? Yeah. Just a second. Can you pass on the? It will switch on, yeah.
Hello.
Yeah.
Okay, so there are structured like sensors used in traditional cameras which do the same task of pose detection and tracking. I mean, they are very expensive,
Yes,
quite
yes,
expensive, and not made that much in India also. So, does it kind of is it competitive or cheaper than that? Is it?
Yeah, this is for this is a good question. So there are what he's saying is there are structured light cameras like Kinect, right? Kinect is an example of a structured light camera. So my Xbox Kinect, it was very famous. It also detects pose of the person and everything, and they achieve real-time performance. But the drawback with doing with the normal cameras, what is the primary difference? I will start with the difference before the drawback. Okay, so if you do with normal cameras, so the normal cameras just sense ambient illumination which is hitting it. So normal cameras which we use, the CCTV cameras, everything is a passive device. So this structured light device like Kinect and Intel RealSense and some lidars, right? Velodyne lidars and everything. So what they do is they throw some pattern on the scene and then get its reflection, do some triangulation to get the depth. Right? They don't. That way they are faster, but they are active in the sense that they are throwing something on the scene. They are active sensors, we call it. Okay. So one difference is what I will ask you a question like, what is the theoretical limit on the amount of like the depth of the object at which you can sense the pose in the traditional this Kinect and a normal camera?
I don't know about the limit actual values, but
No, just to take a wild guess. No?
A meter, I guess.
Yeah, so few meters, right? But this normal cameras, this monkey center I showed results, right? This one, they are at least like 50 meters or 30 meters away. So whatever you see, you can detect the pose using the normal camera.
Okay.
But the depth to which you can throw this active illumination, up to that only you can detect the pose in terms of active sensor. There is a range limitation, right? But you can say that, so you know the setting, like it is 50 meter, 100 meter, I will throw light that much, I'll have a device which will throw. The problem is the device becomes bulky. So you need to have the battery big enough to hold that much energy to throw light to the larger distance. So if you take a Faro sensor, 3D scanner, that is much bulkier than a Kinect, which is very this thing, right? So the battery will drain out. So you cannot monitor over the day. So you need to keep recharging, replacing, and everything. So for the active sensor, that is this thing. Or you need to be plugged in always, and you cannot install it at every places, right? Mm-hmm. So that is the primary challenge of these devices which are active sensors. One is the range limitation, another is this thing. But real-time performance they will give. You can go to 200 frames per second also they may give, because directly you get, so you don't have to process the image through a AI algorithm like we did to get the pose and everything. So there directly you have some pattern you throw and then you map it directly to the pose space and then you get the pose. So that is much easier because inherently they work in the 3D space, so they can easily get the pose because the reflection you can directly get the 3D. Here we don't have the third dimension information, so that's why we told like we don't have the 3D information, but still with image only, how to accurately get the pose and track them in terms of self-occlusion and clutter or some kind of occlusion by the other objects and everything. So that is this thing. So we cannot compete with them, but there is a limitation to those devices also because of the range limitation. You cannot deploy it in the wild.
And these new like ML-based devices are economical to compare to.
Yeah. So always these devices you can use. So whatever you see, you can predict this thing. So you need higher resolution sensor. Even CCTV cameras have become cheaper, so you can deploy them, or even like even some if you want to for the lab settings, you can even have a DSLR kind of device with or CCTV or high-end CCTV also would do it. That is fine actually, but they will not be that expensive as this. As the for an example, Faro scanner would be costing you like 60 lakhs and everything. You have Velodyne scanner some 30 lakhs and everything. So they use it for the these autonomous vehicles and all. They use those lidar scanners. Okay.
Thank you.
Any other questions? Queries? Yeah.
Yeah, hello. Hello. Okay, so I was really interested in the fact that you can actually get the synthetic data from rigging a model in Unity, right?
Yeah. That's the next work I will present it actually.
Right. So, so I was wondering if the other way around is possible. So now that you have the pose estimation, you can create a skeleton and you can rig a 3D model of the object. So that way you can actually save time and effort instead of manually rigging something.
Yeah. That is the next I'm going to talk about. Actually.
Okay, so the other way around is possible as well.
Other way around in the sense?
So you have the pose for a object, right? For any structure. So can you actually use the pose to rig it onto a 3D model?
Pose to animate it?
Yeah. So,
yeah, you can do that.
Okay.
So I'm going to show some results. So you can buy some avatar, detect pose from a human and animate the avatar.
Okay, that's actually really interesting.
That is standard thing, yeah.
Hello, sir. I have one question. Any challenges faced by the model while detecting or tracking underwater species like fish?
Underwater we have not tested. So that is a that data set it's not trained on, but if some data set is there, it's good to check it actually. I think it is there. This marmoset, I don't remember. Marmosets are not underwater species, so we have not. Fish we have tested actually. So in that we have trained it, so it should work if it has been trained on fish. So it should work actually, but I don't have results to show. Okay. But other species like fish, it is trained, so shark or something else. That's a good thing to look at. So whether it works or not, but it should work. Because it has been trained on almost all the best data sets we are having. So it would be a linear combination of those poses only. So some new video you showed to them. Any living organism which moves, it can detect and track it. Pose by pose track. Yeah.
Sir, I have a doubt on the previous paper that how to calculate the density of the vehicles.
Oh, this one. Oh, the previous work I presented, yes. This one.
Yes, sir.
How to calculate the density? So you have a bounding box, right, of the vehicle. So you assign some score to it. And the score dies down after some time. Okay, the current vehicle has paused, so it will have some influence over the lane for certain amount of time. And more vehicles are coming on and on and on. It will be a linear combination of that weights. So if the particular lane has more vehicles keep coming, that means the weight assigned to that lane, the area spanned by those vehicles will be higher. If there is no vehicle for a certain amount of time in the particular lane, it will become no weight will be there. No attention will be there in that, you can say. Or no heat map will not report anything in that. Yeah.
So, sir, you using the different method in the right side, middle of the image. Sir, in the middle of the image, vehicle density analysis. That was
yes. There is a different method. Yeah. So we have a framework actually, so which we do it, but the last thing we can The vehicle tracking, after that, vehicle flow analysis, vehicle distribution by lanes, vehicle density analysis, vehicle speed analysis. So there is some processing involved actually. So it takes out, after the vehicle is tracked, the tracking information is used to estimate all of these, like vehicle flow analysis, vehicle distribution, vehicle density, vehicle speed. So that I have not shown. Some more algorithms we built for each of this. Yeah. Any other doubts or queries? Yes, yes. Can you pause? Yes.
Hello, sir.
Yes.
I just wanted to know potential application of post estimation. For example, in Parkinson's disease, can it be applied to predict the falls and the falls of this by
Yes.
tracking the gait movements or something?
Yes. Definitely. It has all the motor activity based research and neuroscience, neuro-driven motor reduction in motor capabilities. It can be analyzed using this method.
Okay, sir. Thank you, sir.
But yeah, so as I said, we are solving a fundamental problem and give it to the community, and people can adapt for different kind of applications. So that's how most of the work we do in the lab or something like that is one of them. Yeah.
Sir, I actually had the doubt in an architecture that what was that GSM net used for?
This one.
Yes.
Yeah. So you go through the paper now. I would tell you, I don't have the entire information in the slide actually. I have put it in archive. You can go through it and mail me if you have.
Sure, sir.
Okay.
Okay.
Any other? So after acceptance, we are planning to release the code also. So you can, you will be able to understand it. Okay. So next work, which I wanted to talk about is this L3D pose, lifting pose for 3D avatars from a single camera in the wild. So this was presented last month in ICASP, and this is a very simple problem. So input is a video of a person who is pose need to detect, and then in the 3D space, we need to have the pose of the person. So all the work we saw in all the methods we saw in the previous work are only working in 2D space. So how to correspond from 2D to 3D? So one question he asked also, the Kinect kind of thing. It's an active sensor and it's a 3D sensor, so it can detect the 3D pose actually. So how to create a Kinect-like system with just a normal camera? You can think of like that also. Okay, but as I told, so acquiring 3D data from the human subjects is so relatively easy. Someone wears a suit and does some activities. You get there are sensors in the suit which gives a 3D ground truth for you, and you have a video camera shooting that person, which will give you the 2D information. So you can easily correspond and use the 2D information to refine that pose and all those things you can do. But what about animals? Right? Because these kind of animals cannot wear the suits and everything, right? So the equipment may be damaged, because one suit we bought from Rococo, it costed some 15 lakh rupees. So you cannot do that. And animals come in different sizes, shapes and everything, right? So you cannot have one suit fitting all the animals to do that. Or you need to have some facility like Vicon and other expensive systems which have multi-cameras, tracking and everything, so which are quite expensive. So can we do something with only normal consumer grade mobile camera or a CCTV camera? That's the idea. So can we achieve that kind of result for even animals? This can be done for humans also, but we are focusing on animals in this thing. So how to generate a training data? First we need to see, because animals cannot wear suits and everything. So how to create synthetic 3D data which could aid the 3D pose estimation, right? So pose lifting is this. So finally what we want to achieve is, given an animal, this is not a synthetic animal, it's an actual animal whose image was captured. So detect the key points, get the pose, and then if you buy, to see whether the pose is correct or not, you buy an asset or avatar, and then make the avatar and rig the avatar to take this pose. So this is what someone was asking, like one of the questions you asked, like can you use the pose to animate something? So that is a simple thing. So you can verify it. Okay, so so we want to establish a mapping from the 2D key points to the 3D space that is entirely independent of both image data and camera parameters. So how to do that? So that we can do by creating synthetic data. So these are some monkeys which are rendered in a synthetic environment, right? In a forest-like environment, in a Unity, right? Or some VR generating tool we use, right? So we establish the correspondence between the synthetically rigged avatar skeleton with the wide 2D poses of the man. So you can render these frames of this thing also and then have the correspondence. Okay, so so we render the key points from multiple views and create the following training pairs: 3D pose from the camera view, which is called soft 3D pose; the projected points on the 2D image space, which is the 2D space, 2D pose, and all the skeleton joint locations, which we call it deep 3D pose. One is the refined 3D pose, which is the deep 3D pose, and the 3D pose which just comes from the view, we call it soft 3D pose, right? So this is a view from a camera following the avatar from a fixed distance at back. So from the back side, this avatar is doing some activities, we keep rendering. So we can easily get a data set out of it, right? Because we are replacing this 3D environment and the animal in the unlikely setting that the animal has to wear a suit and do some activities. So whatever activity we intend a physical animal to do and record data, we are letting this avatar do it, and then have the 2D, 3D correspondences. Okay, so these are the different poses which we use. So there are two data sets we created, one for macaque and another for horse. We call it deep macaque and deep horse, right? So these are the different poses, and these are the different key points for macaque and horse. So the key points vary, like 17, 29, 13 for macaques, and I think one should be horse actually. 6,000. This should be horse. Sorry for the error. So if you see in a large space, like you have the pose recorded, the key points, and this actual pose of the animal. If you see, all the similar poses are clustered together. If you see this hit left, all of them are here. It just turns left, right? And turn right, all of them are something like this, and so on. This gives a hope that doing this, we will be able to generate poses which are similar to the poses from the rigged model, and then use them to animate a new 3D avatar, or detect even poses from in the wild images properly, right? So this is some just a visualization of these key points, and so this is the entire proposed framework. So what it does is, we have a 2D pose estimator which detects the pose. This is the inference phase, so where we detect the pose, and then the key points are pruned to 13 key points, and we have this L3D pose, which is our network I'm going to show, which will lift all the 13 key points to the soft 3D pose, which is going to be the same the number of 2D key points, but the 3D level, as I showed, there are more key points. So this is densely sampled or something, you can imagine, right? There is a lookup table which densely samples this 3D pose into a deep 3D pose, and then you can animate the avatar. This is the entire framework. This is what you do after the model is trained. So what is this L3D pose? This is trained something like this. So we have a 2D key point estimator, and then the 2D key points are fed to some layers, which are MLPs, and then there is a MHSA block, which I will come to it later, and there is activation linear, and the 3D key points are there. And the soft 3D key points, there is a lookup table which will lift it to the deep 3D pose with more key points. You can animate this avatars using that. Okay, so this I will not discuss this MHSA block. You can look at the paper to understand it. I think I don't have it here. So first, you could animate an object in a virtual environment, render it in 2D, have the 2D 3D correspondence, and train this entire pipeline, right? Then given any new image input like this with clutter also, we are able to first detect the 2D key points, then the same number of key points lifted to the 3D space, and then finer sampling of these key points to get the deep 3D pose, and then animate some object. So if you see the actual pose held by this physical monkey, this virtual monkey is going to have it, or the avatar or the asset is going to have it. Similarly, you can see, right? So this is a climbing pose, so this avatar is also doing that, right? So this is for the horse thing. So you can see similar poses as the physical horse, this virtual horse is doing, or the avatar is doing. It's a very simple idea actually. So this idea is seeded by the fact that how to create data for the animals to lift from 2D to 3D. So we generated data. So from data set generation itself was a tremendous task. We generated data by animating or rigging an avatar in the wild setting, right? And then rendering it, the images and everything, and train the model. And then for any physical image, it is made to work. So these are some of the existing methods, and we are able to beat them conveniently, right? So we split them into 80% training and 20% validation. And the evaluation metrics are mean squared error of the joints and the percentage of detected joints, right? And our attention MLP outperforms all baseline models, and this MHSA block has some attention MLPs. I have not mentioned it, so you can read the paper to understand it. So what is the conclusion? It's a very simple work which gave we hope to the community that for not only for humans, but for animals also, you can use such a framework. As we showed for only 2 species, it works quite well. So you can build it's not a very large scale model, a large scale model which could be trained on several species with the different poses. You can buy avatars. So one reason why we did not do it is we didn't want to spend much also. Each avatar you buy also, it's quite expensive, like $25, $50, you have to buy the avatar. So if you have a lot of funds, you can buy avatars of almost like 100 species also, animate them and build a large capacity model inspired by this work, and then do the same task, right? So I really left it to the community to do it, and we showed it for only 2 of them, like 2 data sets we developed, deep macaque and deep horse, for different settings, different environment settings and everything. So if we want to summarize these 2 works, so one is I discussed, where we detect pose and track it, and another one is the 2D to 3D lifting, and then we did the pose retargeting on the synthetic avatars. So it is analogous. So it is like a pose transfer only, right? You are transferring the pose of a physical monkey to a avatar. The same work we had done earlier called pose transfer, which is in the 2D space only. So person is sitting, and you give a stick the pose, like the skeleton diagram, as if he or she is standing. So can you generate an image of the same person? So it's a similar idea actually, but we are going from 2D to 3D, which we call it lifting. Okay, so any questions? We have sufficient time to discuss anything. So this is what I wanted to cover. So this learning things, most of the parameters, how the network was designed and everything. I think the L3D pose code is also, we have made it public. If you want to try out, you can test it. And the other one, I doubt we have done it. So we can go through it and read it and try it. So because implementation wise, you would be much well versed with the basic courses in deep learning and so on, right? So these are some two recent contributions which we did. Both the works simultaneously happened, and they took around 2 years for us to conceptualize and get them ready and send it for the public. Okay. Any questions or queries? Comments?
Yeah, it's an interesting work. I have a query. When you're converting the monkey's image into the pose, so now we have 17 markers.
Yes.
So are you taking its network information or its spatial information as well? What do I mean by spatial information is XYZ coordinates as well?
Yes. We are using the pixel coordinates, right? Of those things.
Okay.
Spatial information.
So how like when these pixel coordinates are going into the lookup table, what does they suggest?
No, it's not a lookup table. It's a network which is trained, which converts it to from the 2D key points to the 3D key points. It's not a lookup table. The lookup table is for just upsampling the soft 3D pose to deep 3D pose.
Okay, thank you.
Okay, so this entire thing is end-to-end trained. Because we needed more key points to animate, because the model we get will have more key points compared to there is a inconsistency or incompatibility between this model and the detected 2D key points, right? So we want to bridge that gap so that you detect from anywhere, you can animate any avatar. So that's why this lookup table is there. Any other questions? Yeah.
Why not directly use that in the network?
Which
Like the network to discuss.
you can use the mic, yeah.
Like the network is custom, right? So you're getting, I guess, like around 10 points or 13 points, and then looking up to 29. Why not have a 29 output in the?
Oh, okay. But because this soft 3D key points, as I remember, is dependent on how many 2D key points you detected on this. So we keep the same number actually. That is easier for building it rather than having changed for different image. Yeah. So for each of these 2D key points detected, so we want to get the third coordinate for it to get the pose. That is the only job of this. Then after that, it customizes for how to retarget here. Any other queries? Any other works I showed earlier, you have interest, you want to know more, also you can ask. You have some time. Anyone? Yes. Yeah. So EEG to image. EEG to image. Yes. So this one. So this is based on the idea. There are some ThoughtWiz and other data sets where there is a EEG data given and there is a corresponding image given. So what the person was imaging, or they show image to the person and while recording the EEG also.
Is it like imagining the image, kind of imagined recordings, right?
Yeah. There's
picture out there, and you're imagining about it. The character.
Yes. The idea is the person is thinking about that image. So we want to, like, it's also lifting, you can say actually. So EEG is a 1D signal. You are lifting it to 2D. Image is a 2D data, right? So the AI standpoint, if you want to see this problem, it is like EEG is a 1D signal and you are lifting it to 2D space, which is the image. it doesn't have, you cannot get the visual sense of what the person is seeing or thinking at that time. So we want to build a AI model which could take this EEG and then visualize it. So there have been strong correlations we find with the EEG, what is recorded and what image it predicted, right? So based on that, we are trying to build a network which could lift the EEG to a 2D space and make the thought process meaningful. That's how it is. Yeah.
Okay. Thank you.
And one more thing I would point out. So the second question he has not asked. So what if, why not EEG to video? Thoughts are like, you can have you don't have a static image of the person or of the object of interest or anything. It could move also while recording the image. So there is a work in URIPS 2024 called EEG to video also. So we were attempting it, but some other guys did it before us, and you can see that work if you are interested. EEG to video, you refer to this URIPS 2024. And another thing could be EEG to depth, right? EEG to 3D, where you cannot go, right? So that is another ongoing work some of the people are attempting. Because EEG is like, it's a like a 1D signal that normally our human, this thing is about image, video, or 3D animation. So these are the things how our thought works. But strong neuroscientific questions, still people are working on that. And some of the things I would not be able to share now, but probably in the future, some of the ongoing works in our team itself, we are trying to answer some of those questions.
Thank you.
Okay. And yes, any other? That's all. Okay. Thank you for being with me. So I ended up 10 minutes earlier, but it's fine, I think. So it was great to present a couple of works in detail and some other works which we have been doing in this space. And do reach out to me if you have any queries. I will connect to my students also who did this work, so you can interact with them. And glad to talk about it offline also. Okay. Thank you all. Bye.